Cyclohexanone can be prepared in the laboratory by reacting cyclohexanol with concentrated sulfuric acid and sodium dichromate. Ethane dioic acid is added to the reaction mixture in order to react with any of the excess sodium dichromate. This mixture is then distilled, and the impure distillate is going to be a mixture of cyclohexanone and water. We've been given some data here, so we've got our cyclohexanol and our cyclohexanone, and we've been given the boiling points, the density, and the molecular mass for both of these. And for this question, we need to draw a labelled diagram to show how we would safely set up the apparatus for distillation, and we need to describe a method to obtain a pure sample of cyclohexanone from this distillate overall. So let's start by drawing up our distillation diagram. So we're going to start by having a round bottom flask, like so, and this is where our mixture to be distilled will be kept in. We've got to have a heat source below to heat this up. And now let's get to drawing the rest of our distillation setup. So we've got some glassware to connect all of our different bits together. And we need to connect this to a Liebig condenser overall. So we have a delivery tube which runs all the way down to the bottom, and then our condenser will be connected onto this. So it will look something like this overall. And then we have to have some sort of vessel at the bottom to connect our distillate. So I'm going to pick a conical flask. And we need to have a thermometer in our setup. And the thermometer needs to be at the point where the vapours are going to be escaping. And that's so that we're measuring an accurate temperature, and therefore we can determine the boiling points and see which vapours we've got escaping. So labelling this, we've got our thermometer here. We've got our condenser here. We've got a conical flask overall. We've got a round bottom flask, which I'm just labelling as RBF for short. And we've got our heat source. So for example, a Bunsen burner or a hot plate would also be appropriate here. And we also need to label which way the water is going to be going in and out of our condenser. So it's always cold water in at the bottom, and then warm water out at the top here. So we have cold water going in at the bottom, so that when our vapours are travelling down, they then condense at roughly this point here in the system. Because if we had cold water going in at the top, then our vapours would condense at this part, but not fully because they'd still be very, very warm. And then when the warm water is then travelling out, this could then potentially evaporate our liquid again. So it's cold water in at the bottom and warm water out at the top there. So now we need to describe a method to obtain a pure sample of our cyclohexanone from this distillate here. So we need to think about our further purification steps. So we were told that our impure distillate is a mixture of cyclohexanone and water. And what we've got here is we've got an organic compound and an aqueous compound. Therefore, we can use a separating funnel to separate these two out. So we can separate these into an aqueous and an organic layer. And the reason that we can do this is because our cyclohexanone is less dense than water. So we know that water has got a density of 1, and we've been told that cyclohexanone has got a density of 0.948. Therefore, it's less dense than the water, so our cyclohexanone will be the top layer, and the water, that aqueous layer, is going to be the bottom layer. So we're going to use our separating funnel, and we're going to tap off the different layers there. We can collect these into conical flasks, we can label them so that we don't get them muddled up. And now, once we've got our organic cyclohexanone layer into its conical flask, we can add a small amount of magnesium sulfate to our cyclohexanone. And the magnesium sulfate acts as a drying agent. So this will absorb any little bits of water which have been left in that layer, because often when you're tapping off the layers, we could leave behind a small amount of that water in the organic layer. So this magnesium sulfate is just going to mop up any excess water there to make sure that we've gotten rid of all of that water. So then our next step now is going to be to redistill that cyclohexanone to make sure that it's 100% pure in case it contains any leftover cyclohexanol as well. So we're going to redistill the cyclohexanone, and we want to collect the fraction which distills at around about 156 degrees there. But it could be anywhere between 150 and 156 degrees there. And for this question, it is a quality of written communication style question. So what that means is that this question is banded. So we've got band 1, band 2, and band 3 for our marks. So rather than just being 1 mark per point, we've got to have an answer which includes some information on our apparatus for distillation and at least a part of a method for collecting a pure sample of the cyclohexanone in order to get into the top bands overall. And some of the indicative points that we need in order to gain some marks and get into the top band for this question are going to be this detailed diagram here of our distillation. So including our round bottom flask, a collection vessel, having our condenser with the correct direction of water flow, having a thermometer with that bulb at the correct exit point for the vapours there as well, and having a heat source. And as well for this whole system to be open. So to have an open system is really important because we need to make sure that these vapours are allowed to exit the system in order to be condensed. And for our further purification steps, some more of these indicative marks are going to be using our separating funnel, where we're also going to be shaking the separating funnel and allowing the layers to settle. So allowing the layers there to settle. Tapping off those layers and recalling that they will be separate layers due to their densities. A step to do with the drying of that cyclohexanone, and specifically in order to get into those top bands, we want to be mentioning that we use magnesium sulfate as our drying agent. And then mentioning the redistillation of that cyclohexanone and the boiling point that we're going to be collecting our fraction at overall. And in order to get maximum marks for this question, we need to have a full detailed diagram with all of these details that I mentioned, as well as at least 2 detailed steps for this further purification. Ethane dioic acid removes excess dichromate ions as shown in this equation below. So we've got our ethane dioic acid reacting with the dichromate ions and some acid, and we're producing carbon dioxide gas, some chromate in oxidation 3 plus ions, and some water. And for this question, we need to suggest how we can tell when the excess dichromate has completely reacted with that ethane dioic acid. So the key thing with this reaction is that we're producing carbon dioxide, which, as I mentioned, is going to be a gas. Therefore, in this reaction, we're going to see some fizzing, some bubbling, some effervescence. So when our excess dichromate has completely reacted with the ethane dioic acid, we're going to get a lack of further effervescence. Or we could also say that our fizzing or bubbling stops. So for this question, we just need to mention that some sort of fizzing or bubbling stops in order to get that mark. For the preparation of cyclohexanone, using our cyclohexanol with some concentrated sulfuric acid and sodium dichromate, we can monitor this course of reaction using thin layer chromatography, also known as TLC. And for this question, we need to outline how TLC could be used to monitor the course of this reaction. So what we can do is we can take some samples from the reaction mixture at regular intervals. And then with these samples, we can spot them or run them on a TLC plate with a cyclohexanol and cyclohexanone control. So what we will have is we will have a TLC plate looking something like this. We'll have our line, our pencil line here, and then we'll have a spot for our cyclohexanol control, a spot for our cyclohexanol control, and then various reaction mixture spots along the plate, and you'll probably use several plates. And then we will get our pattern for our cyclohexanone and our cyclohexanol, which could look something like this. And then what will happen is, throughout our reaction, as our cyclohexanol reacts, we will start to see less of the cyclohexanol and more of the cyclohexanone. So you might see a mixture of the two, and then as our reaction is nearing completion, we will only see spots for cyclohexanone there. And then in order to get both the marks, there's one mark for mentioning that we have to take some regular samples from this reaction mixture. And then the second mark is for mentioning that we're going to spot these on a TLC plate along with our controls. And that's so that we can compare our reaction mixture to these controls to see which out of the cyclohexanone or the cyclohexanol we've got in our mixture. For the second mark, you could also mention about using RF values to confirm which samples we've got as well. For the reaction where we produce cyclohexanone from our cyclohexanol with concentrated sulfuric acid and sodium dichromate, we need to plan an experiment that would allow the student to confirm the identity of our pure organic product, and we need to do this by means of a chemical test. So our organic product here is going to be the cyclohexanone, and what we know about this compound is this ends in ONE, so this ends in one, which means that it's going to be a ketone, which was produced by the oxidation of our cyclohexanol. So this was a secondary alcohol, which was then oxidized with our concentrated sulfuric acid and sodium dichromate to produce a ketone. And we know that our ketone contains this carbonyl bond. Therefore, we can confirm our identity of the pure organic product by first reacting our sample with some of our 2,4-dinitrophenylhydrazine, which I've shortened here to 2,4-DNP. This is also known as Brady's reagent, and they would allow either of these for the mark for this bit. And what happens when we react our sample with this 2,4-DNP is we're going to get an orange precipitate due to the presence of that carbonyl bond. And the key thing here is that we're producing a precipitate. So now that we've got our precipitate, we can recrystallize this. And we're recrystallizing our precipitate in order to purify it. And then we can determine the melting point of our precipitate. We can do this using a melting point machine with some capillary tubes for our sample. And then once we've determined the melting point of our sample, we can then compare the melting point to a known value for cyclohexanone. And we could get this known value from a textbook, or we could look it up online from a reliable website. And in order to get the 3 marks for this question, the first mark was for mentioning that we're going to react our sample with 2,4-dinitrophenylhydrazine, and they would also accept if you put down 2,4-DMP or if you put down Brady's reagent. The second mark is for saying that we need to then recrystallise our precipitate and determine the melting point. So you need to have both of these points in order to get that second mark. And then the third and final mark is for stating that we need to then compare our melting point to a known value or a known library for cyclohexanone.